Yeah, I believe it's recording. So, welcome everybody, another Friday. So, well done for making it to session 17. I know it's been a long journey. Since when did we start this actually? I don't even remember. I think it's, is it June or something or before?
Yeah, I think it was late spring.
My goodness. Yeah, it's because obviously the bi-weekly stuff. So this is like a 2 semester type of thing, equivalent, roughly. Yeah. So well done for doing it. Obviously, we didn't start with just group straight. We were messing about with other structures. So well done for making it to this lecture session 17. Before we start, actually, I really recommend you, for those of you who didn't have the chance to watch Bob's amazing talk. By the way, Bob, thank you so much and well done. It was an amazing presentation. I learned myself a lot of things, so I recommend everybody to take a look, watch the thing. It's on YouTube on the playlist. The application of group theory in origami modular design. It has everything. Bob did a great job of not just connecting the theory with the application. There's also a historical context, putting things into history, bringing in history together. All this, it was amazing, Bob. Thank you so much. So it's on the thing on the playlist. If you haven't watched it, please do so. And the slides for the presentation are on the on GitHub, so you can check the course's GitHub page. The slides will be there. It's also, the link is on the description for the video. George, when I do this, can you see the cursor?
Let me go full screen. No, I don't see a cursor.
What about now?
No.
Okay. Anyone else?
It blinked for a second.
Okay. Yeah. No worries. Yeah. Okay. So this is session 17 of, let's see, 20. Let's see how much we can cover. It's possible, maybe optional for those of you who want. Maybe we can add another 2 sessions or something. Let's see. But I think at least by session 20 we should be able to cover decent amount of the final stuff that we really need. So the end goal will be to have you, with the necessary concepts to get into Lie groups and representation theory. And before that, obviously, we had the topology and differential geometry. So you will need this and this in order to take the Lie groups stuff, because Lie groups are topological manifolds, smooth manifolds. So you need. So this actually brings me to the question also that I'll probably send a survey to ask whether people need some time to review the differential geometry stuff a little bit, just to remind themselves what a smooth manifold is before the Lie groups crash course. So yeah, and maybe it will also give opportunity, if we do that, for people to the group theory stuff will be fresh, obviously, but then maybe the stuff about manifold might not. People already forgot. So okay, so we are here finally. So the green stuff is what we completed. So we completed all we need from like abstract group theory, the notions, the concepts. We look at some interesting groups, starting with I think the first interesting structure, a special type of group we look at was cyclic groups, right?
Yeah.
Yeah, so we look at those and the application to them in cryptography. In this case, we played with the Diffie-Hellman stuff, and then obviously Bob also did. We cover some notions like orbit and stabilizer that Bob needed to use in his talk, and now we are in matrix groups. So this is the end, the final part of this crash course. In particular, we will focus a bit on these special type of matrix groups. We won't define them this week, but next week. on the real case, the orthogonal group and the special orthogonal group. And then after we'll make the transition to the complex matrix groups, in particular the unitary and the special unitary groups. For those of you in quantum stuff, these are the groups that you need. So yeah. Yeah, I'm still on. Yeah, I'm still on, right? The slide is running. It's somehow the slide escaped, and yeah. Okay. Okay, so I'll have to stop sharing and reshare again. There's something strange happening with the slides. Broadcast, come on. Let's see. Let's see. Let's see. There is history. Okay, can you see? The slide is back, I believe. Sorry for that. Is the slide back, George?
Yes, slides are back.
Okay, cool. Sorry for that. Yeah. So this is it. This will be the final stage of this Clash course, and then we'll decide when the best for the Lie groups and representation stuff. And before we start with the new topic, I forgot to add this last week. This result, which says given a finite group G acting on a set, we have this beautiful identity here that the order of the group is given by this, is as a product of the order, the number of the order of the stabilizer and the number of elements of the orbit. Yeah. So in other words, the order of G divides this thing. So this is a nice list of results I forgot to add in the previous session. Okay, so that's it. This closes the previous session. I mean the previous section. So let's do a bit of refresher on thing linear algebra. As I said, it's like just a refresher as opposed to going through it. I hope there is no typo. I'm pretty sure there will be typo somewhere, so apologies in advance. So for those of you who have taken linear algebra, whether with the foundation module with us or somewhere else, or you picked a book or something, you know that given an n-dimensional vector space over the reals R, which is what we are interested in this for us. This could have been also a vector space of arbitrary dimension and over an arbitrary field. But in our case, we are interested in the reals, and we are interested just in finite dimensional case. Okay. So anyway, so a map L from V to itself is linear if it satisfies these conditions. I'm pretty sure most of you on this you have seen this. Yeah. So there's a comment there. Yeah. So maybe I didn't name the previous theorem correctly. Yeah. I actually think it's the Bernoulli style. Yeah. Yeah. It's maybe lemma. You are right, Bob. Maybe lemma is right. The right connotation for it. Yeah. A lemma is also a theorem. Yeah. Okay. So going back to this, I will update the slide actually to reflect that. So Bob is talking about this. Maybe I should put this thing as a lemma, the orbit stabilizer lemma. Okay. So he's saying, okay. Okay.
Yes, this is the orbit stabilizer theorem. Burnside's
Yeah,
lemma
that's
is
right. Yeah,
used to prove
yeah.
it.
Okay. Okay. Thank you for clarifying. I'm confused myself. I was a bit confused because I'm thinking about another topic and coming back. This is what happens when you jump. Yeah, and there are so many like this as anyway, like in this type of things, there are so many results, name with the different names and all this stuff, and it's a bit confusing to keep up.
There's actually a meta theorem that whoever the theorem is named for is not the originator.
Yeah, probably. Yeah, exactly. Yeah. So it's very easy to mix up.
Goes back at least as far as Cauchy. And
yeah. Okay, so let me go back. Thank you, Bob, for bringing this thing. So let me go back again to this. So given here we are interested in finite dimensional vector space over the reals, but this could have been infinite dimensional vector space over any field. Okay. So a linear map, in this case, we are interested in a linear map from V to itself. And another thing is the linear map doesn't need to be V to itself. It could have been from V to another vector space. Okay. But in our case here, we are interested only in the thing for the purpose of our coverage, our session. We are interested only in linear maps from V to V. Okay, so a linear map satisfies these two conditions. This is like a kindergarten stuff for all of you here, I'm sure, on the thing in the audience. So yeah, you know what a linear map is. And you also know, this is just my notation. So let lin of V be the set of all linear maps from V to itself. So the claim is that given two linear maps, L and L prime, their composition is also linear. Okay, so the composition of two linear maps is linear. Okay, I claim also this is from this is like very like kindergarten stuff for all of you here. Yeah, but nevertheless, if you want to play around to prove it, it's like just to warm up. Yeah, you can try to do this. Yeah, and this is just a side note. You can obviously equip this set with a vector space, with a real vector space structure. Indeed, you can actually equip it with the ring structure. Yeah, is a very interesting thing that we won't go over. But yeah, just as a side note here, we are not interested in that in the structure of this for the time being, but just as a side note. Okay, so this is the thing. So the composition of two linear maps is linear. So let's move on to the next thing I wanted to share, which is this. So let's define this set GL of V to be the set of all invertible linear maps. Okay, so a linear map is a member of it only if it's invertible. So the claim is this set that we call GL of V is a group under the composition of maps. Okay, so this group is known in the literature as the general linear group of V. Okay, there will be a confusion here later, but in the end, the isomorphism will connect these two things. So this is the general linear group associated with the vector space with the V. Okay, and obviously, as I said, for our purposes, V is finite dimensional. However, even if V is infinite dimensional, obviously this is it. Okay, the operators are still like linear operators. They still form a group. So they are also very interesting to study. And here's the first challenge. This might be trivial for a lot of you, but nevertheless, even if it looks trivial, try to construct to prove or disprove. So the question is, if given two vector spaces, V1 and V2, real vector spaces, is it true that if the two of them are isomorphic, it then follows that their underlying, their corresponding linear group are isomorphic from a group theoretic sense.
The wording there is a little unclear. You say isomorphism of two vectors. I think you mean isomorphism of two vector spaces.
Oh, vector spaces. Yeah. Sorry for this. I will correct this slide. Yeah. Isomorphisms of two vector spaces. Yeah. Implies isomorphisms of their corresponding general linear groups. Yeah. Sorry. Thanks for the thing. I'll correct this before I upload this slide. Yeah. So this is a little challenge. What we're feeling is this. Who thinks this is it true? Who can see this easily? It's true, and who is not sure?
Check the chat.
It might look like trivial, but this is just to see the relationship. One structure, which is the linear, the vector space structure, then having something to do with the structure on the group side.
Yeah, it actually is kind of important to note that you need all of the vector space structure and all of the group axioms for this to work. Yeah. A big hint is that it's not all the linear maps, just a special subset of the linear maps.
Yeah, correct. Yeah. And very interestingly, Dimitri is saying if the vector spaces are finite, I can see it. So if we have like finite dimensional vector spaces, yeah, maybe that's the thing. When you go to James's course, that will deal with Hilbert spaces, specifically dimensional Hilbert spaces. I'm taking here. I mean, you can think about this like I'm taking here like yeah. Go ahead.
I think there's a subtlety there, the difference between a linear space in general and a Hilbert space that makes a difference.
In the infinite dimensional realms, things are very strange. Yeah, because you have to take into account things with the countable and uncountability. All this stuff is like, yeah. Anyway, yeah. So let's stick with the finite dimensional vector spaces. So yeah. So I challenge you to try to see this. So there's a typo here. It means to be two vector spaces instead of vectors. I knew I had a typo somewhere. So I'm keeping up with the tradition of having typos, and it's actually good that people are spotting them. I think actually I would use this as a strategy. It was like by accident making typos, but maybe by strategy to insert to see whether people are paying attention. Okay. So now here's another. This is more of a notation refresher and some facts. Let's see. I hope I didn't make any typos here as well. We'll see. So by convention, we will write Mn of R to denote the set of all n by n matrices over the reals, or matrices with the entry, n by n matrices with the entries as real numbers, with the real numbers as entries. Okay, but this is not a standard, like it's like a preference. Some people use this instead of this. Some even use Rn times Rn. I've seen that as like more of an old school notation. I had a professor who used that notation instead of yeah. So it varies. For in our context here, this is the notation that we are fixed. And also, I'll assume everyone knows about obviously the basics of multiplying two n by n matrices. Addition. Transposition, taking the transpose of a matrix. Yeah, George, you were saying something?
I was just going to say a little minor challenge. If you have n by m matrices rather than n by n, what's the difference?
Yeah. Yeah, that's interesting to think about. Yeah. So I'm making life easier for us, because this is the shortcut for what we need is obviously we need the square matrices. Yeah. Now, here's the thing, a little challenge that we'll go through here. When equipped with ordinary matrix addition and multiplication, so I'm assuming that you know what they are, the question is which algebraic structure Mn of R forms? Let's go one by one. Does it form an abelian group under addition? Yeah. Who wants to throw the hat? I know this is like very trivial, but there might be someone else on the audience that might not see this. I believe everyone. It does, right? Yes. Anyone agree? Yeah, and it's abelian. Okay. And now the second question is, does it form a non-abelian group under multiplication?
Not
You have to remember the
necessarily.
group axioms. You need to remember, this is where this is a test to remember the group axioms. So if it fails in any of the axioms, it means that of the group axioms, then it's not. So let's see. So I'll gamble, say it doesn't. Does anyone see where it fails?
I disagree. For n equals 1, it is abelian. For n equals 1, multiplication of matrices is abelian. For n greater than 1, not so.
Do you agree with that? The correction, maybe I should have added n greater or equals to 2, for instance. Yeah? Are you sure, George?
For greater than 1, I agree it's non-abelian.
But is it group at all, actually?
Oh, that might be. Yeah, I think that follows from linear algebra, the relationship between matrices and linear transformations.
Yeah, but this one here, we will come to the relationship, but this one, this matrix here, you know, we are just considering, you know, the square matrices under these binary operations, in this case, the multiplication of matrices. So this includes all the matrices, including the zero matrix. So I think I already said.
Oh, oops. No. Oh, I missed that. I should have caught that.
Yeah, no worries. I know it's very tricky. The way I put it, it's a bit confusing. That's why I added it. So it's not a group because it fails.
Oh,
Groups
no, they don't even need to be 0 to be non-invertible. Yes.
Yeah. You need every element to be invertible, right? You know, and we know that there are some matrices which are not invertible. So therefore, this is not a group. Now this one here. What about a real vector space of dimension n to the 2, n squared, sorry. It is a vector space, right?
Yes, if you kind of stretch it out instead of thinking of it as a square, stretch it out into a line of 4 elements or n squared elements. Yeah.
Maybe here I have to add, I forgot, because here I'm just considering the actual, you know, binary operations on it, but there is also scalar. I needed to add here. With the scalar multiplication, is this a vector space? That would be more. Yeah, it is a vector space, yes. And as a dimension, I claim this is the dimension of it. Or did I make any mistake? Anyone agree? Yeah.
Okay. I had jumped ahead. Okay, sorry.
Okay. Now, it's very important. It partly comes in with what George was saying about the connection between matrices and linear maps. So from linear algebra 101, you know, so given this is not something that we will show here because obviously we don't have time to show that. So you have to remember the foundation module or pick a linear algebra book. So essentially, given a obviously this a square n by n matrix, the matrix, this induces a linear map, right, through the matrix multiplication. The thing through multiplying through column, the column matrix, for instance. Okay, so that's linear. That induces a linear map. Let's call it L subscript A from Rn to Rn. Okay, here we are assuming that Rn is obviously equipped with the canonical, the ordinary matrix. Sorry, the ordinary vector space structure that we all know about. That we learn about. Yeah, and likewise, given any linear map, okay, from Rn to Rn, this induces a matrix that we call A subscript L, which is an n by n matrix. So this is essentially telling us that linear maps on Rm are the same thing as n by n matrices over R. Okay, so this correspondence, when you are dealing with n by n matrices between matrices and linear maps, this is very useful, because it means that if we want to do something with the linear maps on Rn, we do it on matrices because we know how to compute matrices, right? So okay, so we are good with this, and now we are going to define the notion of real matrix groups. Okay, so given a subset G, okay, a proper subset, I'm assuming here because Mn of R, it cannot be group, so it has to be a proper subset, is a matrix group if it's a group under the ordinary matrix multiplication. So not addition. So we call a subset of Mn of R a matrix group if it's a group under the ordinary matrix multiplication. So not addition. It's also it might be under addition, but we are not interested in addition. We are interested in multiplication. So this is what we call we say it's a matrix group if it's a group under matrix multiplication. Okay, and obviously this means first of all if it's a group, it means that it has a binary. The multiplication then is a binary operation on it, so it's closed, right? It's a closed binary operation. So if you have two elements of the group, I label them A, B in G, then their product is also in G, right? And also this is trivial. The associativity also, if it's a group, it obeys associativity. This is trivial to show because we know that the operation in Mn of R is associative. So that's pretty straightforward. And the identity matrix must also be in G because to be a group, it needs identity, and it must be the identity matrix. So you can also show this easily that it must be the identity. It cannot have another identity because that would imply that there's another identity, two identities on this, which is not the case. And most importantly, for any matrix in G, there exists an inverse. Okay, so this is a matrix group. Okay, so now because it's a group, a matrix group is a group. We can ask any questions that we were doing, in abstract sense. All the constructions that we did, actions, left, right, coset, orbit, stabilizers, and so on. So we can, bring all these notions in the context of matrix groups as well. And this is what we will do in the next slide. I hope I didn't. This is actually a homework for people to see if I didn't make any typos, especially in the signs. Okay, so let's n be equals 2, so we are dealing with the 2 by 2 matrices, and let's the set G be defined as the set of all these matrices, where this defined like this with this parameter theta in this interval. So the claim is that this is indeed a matrix group. It is, which means that it's a group under multiplication, under matrix multiplication. And as such, as I said, we can bring any other notions that we've been talking about, like actions, for example. I claim that we can build an action, of this group, this group made of these matrices, like this, and this is a group action. Okay. So the question is, another question is, this group is a very interesting group. We won't see this until in a thing. Can anyone see which group is this? Apart from George. George knows. If nobody else knows, George will tell us.
Well, one can
Anyone?
make.
Okay, Dimitri also knows. Okay. He knows, yeah. Okay, so maybe let's see. George, do the honors, and then we'll see if Dimitri agrees.
Well,
Dimitri is not on stage.
If you recall a little trigonometry and analytic geometry, you can see what this is just as a subset of R2, and the basic little trick will show you that it's a little trig will show you that it's a circle. And the fact that sine squared of theta plus cosine squared of theta is a constant equal to 1. And that is the definition of a circle. If you think of x and y as coordinates, and x squared plus y squared is constant, that means the distance from the origin is constant and equal to 1. So you have a unit circle.
Okay. And this makes this group what? Okay, so there's someone else on the chat as well. So Barry, rotate.
Barry, thank you.
Do you all agree? Dimitri, do you agree? George, you agree? This is then this group. This is a group of rotations on the plane.
And this actually shows where the term orbit comes from. The circle is the orbit under the group action.
Yeah. Okay. So there you go. So we are on saying everyone is on the same page. Yeah. This has a name. We'll do it in the next session. But just for you to see, now it's becoming more. I know George was saying that he's more of a geometric person. So this is now coming. This is his home turf. It's bringing the algebra more into the realms of concrete of geometry. Okay.
Yeah, and Dimitri is correcting me that technically a circle is a path on the vector space itself.
And now here's an interesting challenge. This might be a trivial challenge for most of you as well, but I challenge you to try to do this to see what's happening. To play with it. So consider G to be the group, the rotation, the group that we defined previously. This group. Okay. And so the question is, the challenge is, you are encouraged to identify the orbit for these elements. I guess this is this is straightforward. The orbit for 0, the stabilize, and so on. But these two, they might give you something interesting, and they happen to be something very interesting because in relation to R2. I know some of you who remember linear algebra. You will know what this is. The two of them, they form something. Let's see what actions. Yeah, go ahead.
That they might give you a little more structure than just the Cartesian product structure of X and Y.
Yes. So I encourage you to go and try to compute this thing and see what happens. As I said, I keep the tradition of anytime we go to a new topic, we start very easy. And now we define the general linear group of a vector space. Now we are defining general linear group over the reals, over the field of reals. Okay. Notice the difference in terminology. The other one was the general linear group of V of the vector space. This one is over R, over the field itself. Okay. Well, in another slide, you will see actually it doesn't. In a sense, it won't matter because of one result, but you will see in a minute. So now, for the time being, so this is defined like this. So this is a subset of n by n matrices whose determinant is non-zero. So any matrix that's n by n matrix with the non-zero determinant belongs to this set. So the claim is this is a group under ordinary matrix multiplication. Okay, and here's a hint here to prove this. For example, if the determinant of a matrix is non-zero, then it's invertible. In fact, a matrix is invertible if and only if the determinant is non-zero. Okay, and this group is known as the general linear group of order n over R. Okay, or just general linear group. Okay, and there's also the notation depending if you pick a test book. Some people use this notation here, GLN of R. I prefer to use this. Funnily, even though I'm using this MN, the M is on the thing on the outside here. In here, I prefer to use this. It's a little bit more cleaner, especially when dealing with subgroups of this and so on. For me, anyway. But it means the same. Some people use this terminology, this notation. So, in general, this is. I hope you can see. This brings us to the other question that George we were talking before. In general, it's non-abelian. In general, okay. So the question is, then you can ask another question: is under what circumstances is it abelian? But in general, it's non-abelian. Maybe George can.
Yeah, well, even just from the group theory point of view, without the vector space, you can find abelian subgroups sometimes. We've seen this even with the permutation groups,
yeah,
and cyclic groups.
Yeah. So is that my connection breaking or am I on?
I hear you.
Okay. Yeah. So again, this is a group, so we can ask legitimate questions that we can ask about group. Apply all the constructions that we did. Like ask about actions of this group on a set, for example, on Rn, for instance. Left, right coset, orbit, stabilizer, and so on. Okay. And very important. This is why this we are covering this. This group is actually a prototype of a real Lie group. So this is a good example of a Lie group. Okay, a Lie group of dimension n to n squared. Okay.
If you recall your topology and geometry, Rn is itself a smooth manifold.
Yeah, and this is a smooth manifold indeed. Yeah, you will be able to see more this. How come this is the thing if you are not able to see this? But this is it's a smooth manifold. So therefore, that's why it's a Lie group, because it's a manifold. It's also a group. Actually, it's not that. That's why there's also another condition, which is the multiplication and these things. Having to specify the other conditions like we won't go there. We save that for the next course. Okay. The reason why it's a Lie group and it's the notion of dimension stuff. I think this comes from the manifold structure. You will learn this in the Lie group section. Yeah. But this is a very this is the example of a Lie group. Okay, real Lie groups. Okay, because we are talking about real real matrices, matrix groups. Yeah, and now this can tell you that there are also complex complex Lie groups as well. So okay, and now this very important theorem. This is the last slide, and then I think there's a challenge. So let GL of Rn be the group, the general linear group, the group of invertible linear maps from Rn to itself. Okay, where obviously Rn is equipped with the ordinary vector space structure over R. Then the claim is that this group is isomorphic to the general linear group over R. So the two things are the same thing. Okay. So this is very interesting. If they are isomorphic, it means there is at least an isomorphism between them. So this is what you need to show. You need to construct an isomorphism. And as a hint, you can use the canonical basis to do this. With a bit of linear algebra stuff, you will be able to prove this. And another thing I forgot to add, if you do it using the canonical basis, try to use another basis and do the same construction and see what happens. So use the canonical basis to prove the isomorphism, but try to construct an isomorphism. Try to see the using another basis, because Rn doesn't just have the canonical basis; it has other bases. Okay, and now here's a challenge. This challenge here: is it true that any matrix group is indeed a subgroup of the general linear group over R? In other words, the general linear group over R is the largest possible real matrix group. So everything else contained is contained in it. So this is the challenge for you. And that's it. These slides, I will correct some of the typos that we uncovered as we were going through the session. This will be available on the thing on GitHub afterwards. The slides, the YouTube recording. Hopefully, I will be able to do it over the weekend. Let's see. If not, maybe by Monday we should have. And so on. Follow us on LinkedIn if you are on LinkedIn, just to make this community the awareness to increase. To make mathematics more accessible to other people who might use it to contribute to advancement of not just science but also technology. Yeah, and that's it. Is there anything? Let me go back to this last slide to see.
All quiet on the chat.
What's your feeling about Talent 3? Is it true that every subgroup, every matrix group is indeed a subgroup of the general linear group over R?
I think so, but it might be rather tricky, or remembering all of the details not to go wrong to actually prove it.
Yeah. Well, Dimitri is saying it's sort of in the thing by definition, it's sort of already implied it's like trivial. So the challenge is for the others to, yeah.
I think the heavy lifting actually is in theorem 1.1.
So yeah, so this is our, George, you were seeing something?
Dimitri is also saying we kind of defined it this way.
Okay, in that case, it's true then. It's true then, according to Dimitri. So the question is, everyone else can see this. By definition, right? This is the set of all invertible matrices, right? So,
I kind of see that every matrix group is isomorphic to a subgroup, so maybe that is all you need.
Yeah. Okay, so that's it for today. I know we are like 7 minutes thing, but this is it. We are starting from from very basic. And then in the next session we'll cover more stuff. In the context speaking about Lie groups, some other like subgroups of it, that are also Lie groups, like the orthogonal group, the special orthogonal groups. These are subgroups that are also very, very important, in variety of applications, and so on. So yeah. So this is really the thing. For the purpose of Lie group stuff, if you feel comfortable with this, you're already like halfway through it, Yeah.
I mean, I propose, since there aren't that many challenges, that if we have a study session, it be an opportunity to review the linear algebra basics.
Yeah, especially these other challenges, like what is it? These things that maybe you need to, like here, for example, to show that any linear thing is indeed. There's another one. This one as well. I think this is like obvious. It looks like there's another. Where is the other one? Yeah, in here. Yeah, like to prove their isomorphism, because this will obviously you will need, as I said, it's easier for you to do it with a canonical basis. You choose the basis in order to construct your isomorphism, because you need, for them to be isomorphic, it means that you need to show there exists an isomorphism. So, and to add to that, I want if you do it, it would be nice for you to pick another basis and try to construct the proof using another basis that's not the canonical, to see what happens.
Yes, that right there is a very big hint.
Yeah. So yeah. So I'll stop recording and